Yeah, 그 리코드 해주시.
Mm-hmm.
Okay, so I look in a weird position, but okay. Sorry for the mess.
No problem.
So,
It's Zoom. Zoom is always like that.
so today's speaker is Dr. Alexander Vikman from Institute of Physics of the Czech Academy of Sciences. And today's title is Lower than freezing water couplings can still generate dark matter and be measured via gravitational waves. So please begin.
Okay, so thanks a lot for invitation. It's my pleasure to be in Korea, even virtually, even on Zoom. And let me tell you about some activity which we had here in Prague, and not only in Prague. And feel free to interrupt me at whatever time if you want to ask anything. All questions are more than welcome. Okay, do you see my slides? Okay, I see that you see my slides. Very good. So this talk is based mostly on these two relatively recent papers, which are done in this very nice international collaboration with Sabir Ramazanov, who is also in Prague, with Zhenya Babyshev, who is in Paris, Dima Gorbunov, who is in Moscow. And I think the major driving force behind this project is Sabir, so he deserves most of the credit for this adventure. So let me tell you immediately what is my main message. So my main message is the following, that there are inverse phase transitions, and it's not that well discussed in the literature to our mind. And this inverse phase transitions is a novel way to obtain non-thermal dark energy, even for those extremely feeble couplings when even freeze-in does not work. So it's really what we are going to talk about is a scalar field dark matter sector coupled to kind of thermal degrees of freedom with really fantastically tiny couplings. Okay. And nevertheless, it can be dark matter. Then this inverse phase transition actually allows to have domain wall network in the early universe. And this domain wall network is what usually people say it cannot be because it will overclose the universe because it does not decay fast. But here, this network actually melts away due to the inverse phase transition, and therefore, you could have such interesting structure of defects in the early universe. Then you see the interesting thing is if you have such defects in the early universe, then they would emit gravitational waves. And what is interesting is that the property of these gravitational waves are kind of simple or relatively simple, depending on how precise do you want to look there. And if these two things are connected, so basically the appearance of this domain wall network with later inverse phase transition, in this case, this domain wall network emits gravitational waves whose properties are sharply defined by properties of this dark matter, in particular by the coupling constants, as you will see. So what is interesting is that this gravitational wave signal can be observable in the near future observations, which is striking, I would say. So basically, what I'm telling you is that there is a mechanism to produce dark matter in a kind of non-thermal sector, which is decoupled practically from us. But nevertheless, these extremely tiny couplings can be traced in gravitational wave observations. So what we are lacking and what we need is precise numerical simulations to determine the proper spectral shape of this gravitational wave signal. So this would be very interesting, but unfortunately nobody of us is a specialist in doing such numerical simulations. So we base our analysis on previous simulations, which are a bit different. I mean, they are done on a system which is a bit different from what we are doing. So therefore, there is some uncertainty there, but we think that there are good reasons why we can apply the results, at least with some reservations. Okay, now let me first start from inverse phase transitions. So as it's well known from an old paper, written classic paper, I would say, by Steven Weinberg, is that what he's writing is that in one case, it is found that a symmetry which is unbroken at low temperature can be broken by raising the temperature above a critical value. So you see, it's kind of ideologically a very strange situation because very naively, we think that high temperature corresponds to UV, UV should correspond to more symmetries. And here, actually, it's vice versa. So UV corresponds to kind of less symmetries in effective sense. So this is quite a non-standard setup in this sense, but nothing is really exotic there. Okay, let me discuss in a bit more details how does it look. So it was at least in this practical incarnation for dark matter was reintroduced by Zhenya Babichev, Dima Gorbunov, and Sabir Ramazanov in 2020. So what these guys considered? Suppose we take a singlet scalar field chi, and it has normal bare mass capital M, and normal quartic coupling, so lambda chi to the 4. So we would like to have Z2 symmetry, so that that gives us more hope for stability of this scalar field. So there is no cubic terms and so on. So we can forbid them by symmetry. So now we add an additional term, namely this mu squared. And this mu squared is kind of contribution, if you want, environmental mass contribution, right? So it depends on some environment, which I'm going to specify a bit later, what it can be. And there actually could be different realizations of what this mu is. What is crucial for us is this mu is mu squared is actually negative. So it's a tachyonic contribution to the total mass of the scalar field chi. So now let's consider different situations. Of course, here what we should consider, what we should compare with is when mu is larger than the mass, the bare mass. And in that case, the symmetry is obviously broken. So the true minima corresponds to non-vanishing expectation value of the field chi. And if this mu is time dependent, then the position of this minimum is time dependent. So now let's consider when mu is less than m. And in that case, of course, the symmetry is restored. And basically, what is unusual in our case is that we say that the picture on the left, so basically when mu is larger than m, is early universe. Then the tachyonic mass decays, so red shifts away due to cosmological expansion, and you appear in this picture, which is late universe now. So in a sense, we flip the order of events with respect to standard cosmological phase transitions usually discussed. And what is interesting is that if at this restoration, the Hubble parameter is less than the mass, then the field oscillates, and that's standard dark matter, like for, let's say, light particles, like axion-like particles, for example. So this is, roughly speaking, the mechanism. Now let's see how does it work in a bit more detailed. So first of all, let's look how can we trace the vacuum. So the minimum, as I told you, moves, and if you want that the field follows this minimum, then there should be some adiabatic approximation. So what do? We take effective mass at the minimum. So this is given by this formula. And then one can think that, okay, this field is like an oscillator, right? It moves with the frequency of this effective mass around this minimum. So of course, then one can create just very standard adiabatic parameter. And basically that implies that you can trace the minimum provided that omega dot divided by omega squared or m effective dot divided by m effective squared is less than 1.
Excuse me?
Yeah.
So in this adiabatic condition, the left-hand side is m dot. Oh, sorry, m dot over m square, not m dot over m.
Yeah.
Dimension is okay. Thank you.
Yeah.
Sorry about that.
No problem. You're welcome. So, then basically, if this adiabatic condition is fulfilled, then the field can sit in this minimum psi min above and just trace it, moves together with it. If this adiabatic condition is violated, then that's it. You cannot trace the minimum anymore. And you see, in particular, it's practically impossible to hold on this adiabatic condition so that the adiabatic parameter is less than 1 if the effective mass is 0. Then there is no adiabaticity. And that happens when this parameter mu is roughly basically equal to m. Okay, so that clearly does not work. But of course, before this m effective gets to 0, because our mu is redshifting, so basically before that it's larger than m. So at some moment it will be the time or the period, basically the moment of the evolution of the universe when this adiabatic parameter is just 1. Okay, it's just slightly before the moment when mu is equal to m. So one can especially see that you cannot follow this minimum because you see you can calculate the velocity of the minimum, so basically psi minimum dot. And of course, when the m effective goes to 0, then naively this psi minimum would diverge, and that's of course not what we are allowed to have. Okay, so now let's see how to calculate resulting energy density. So basically, what happens? We take this adiabatic parameter and calculate when is it 1. Okay, and that gives us immediately the estimation that this moment with indicated here with asterisk is the moment when the adiabatic parameter is 1. And you see it works for generic mu, and on the for last equality or last estimation, I use the point that we assume that mu is redshifting kind of cosmologically, whereas this kappa is kind of slowly dependent function of time or just a constant. So basically, in the scenario I'm going to concentrate on later, this kappa will be 2. Okay, so basically the moment t asterisk is when the adiabatic parameter is just exactly 1. Of course, this is just an estimation, but it's perfectly well confirmed by numerics, as you will see just in a second, for a particular model. Okay, so basically, if this h is less than the mass, then after this adiabatic parameter becomes 1, the field cannot trace the position of the minimum anymore. It detaches from the minimum, and that settles you this oscillation amplitude psi asterisk, right? So after that, the field behaves as dark matter. And of course, you can calculate how does it redshift even later. And it's just normal scaling 1 over a cube. Okay. So basically, again, for this talk, I will use this kappa equal to 2. And it just shows you that this density which we produce is actually inversely proportional to lambda, to the self-coupling constant, which is kind of interesting. Okay, so now you see, we kind of entertained this idea already a couple of times, and you're more than welcome to add to the list. So basically, first, these friends of mine, they studied mu squared to be just Ricci scalar. Okay, so it's just kind of gravity modification, but pretty natural one because, of course, these couplings psi squared are pretty natural. So then, in collaboration with Sabir and Federica Urban, who is also in Prague, we entertained kind of more exotic possibility in a sense, because, well, exotic and maybe less exotic, because if this mu squared or proportional to r was a marginal operator, so to say, here we use an irrelevant operator. So namely, now our mu would be created out of the strength of a gauge field. Namely, here we use electromagnetic field. And basically that implies that we coupled f mu squared to chi squared. And this is, of course, an irrelevant operator from the point of view of effective field theory. So it's suppressed by some cutoff parameter lambda. But what is important here is that it's the most general term you can actually write if you insist that chi is Z2. And it's proper scalar, not pseudoscalar. So what is the idea? That in the early universe, you could have very large magnetic fields. And because this can be the fields which we actually observe now in intergalactic space. And then, of course, blue shifting them by going back in the history of the universe, you could get pretty substantial values. So that for light dark matter, they can trigger phase transitions. Actually, this is not that strange because there are some phase transitions in condensed matter which are triggered by larger values of magnetic fields.
So,
but in this talk,
so this B is the magnetic field in the universe.
Yes, absolutely.
So the sign of in front of this B square is negative or positive?
Well, that also depends how do you properly define it. But the sign in this formula should be such that mu squared is B squared. In such a way that in the formula above, this
usually F min is proportional to E square minus B square, right?
Yeah. No, you're right. Look, it's just put the minus here.
Okay,
good point. Good point. I was just sparing on minuses, but of course you're right. So the important thing is that this mu squared, which is now positive, is B squared. So then, of course, then you would need to put minus. Very good. So now this. By the way, yeah, you're right. So now, so the scenario which I'm going to concentrate on in this talk, and where we kind of looked at gravitational waves, is actually much more standard one. So we don't use any irrelevant operator. We use again a marginal operator. So with dimensionless coupling constant. So basically we couple our field chi to kind of multiplet of some scalar fields phi, which can be even complex. And we assume that this phi has n degrees of freedom. So G squared is our portal coupling constant in that case. We assume that phi is thermal and chi is not. So basically phi was produced during reheating. It participates in thermal evolution of the universe, and chi is not. So now what will happen? So if we just use normal portal coupling constant, then this phi theta phi expectation value will be just proportional to t squared. And therefore, this mu is roughly speaking given by temperature. So then in the early universe, the temperature is high, so therefore mu is large. In the late universe, temperature is small, mu is small. So this is what I'm going to talk about from now on. Okay, let's see again how is it realized. So basically what it implies that we have this portal coupling constant. It's a quartic interaction. And what is important is that this quartic interaction has a negative sign. Okay, so this is what is kind of unusual, but don't worry, potential will be bounded from below. So this is our portal coupling constants. So don't keep in mind that we use this notation G squared, even though this is just a constant. Okay, this is repetition of what I said before. This mu is just this. And of course, it's just this for temperatures much larger than the mass of phi. So in the relativistic regime. So now, so is this inverse phase transition time we estimate very easily when mu is just equal to m, just in order not to calculate properly this when the moment of time when the adiabatic invariant is just one, sorry, adiabatic parameter is one. So we just looked at this mu proportional to m, sorry, equal to m, and that gives us immediately the moment of the inverse phase transition. So as you see, it's proportional to the mass, and then we divide by this g. So basically, that's we would know immediately when this transition should happen. So in reality, it happens by slightly higher temperatures, but not much higher. I mean, like it's just some numbers. Okay, so what is kind of interesting? So I told you this naive estimation, and now what one could see is that the following statement is true, that actually the dynamics of such a system in approximation when this chi, which is supposed to be later dark matter, in the very early universe, it's completely subdominant. So therefore, we test, so to say, field approximation. So then the basically equation of motion for chi will be given by this formula. I mean, normal motion. And the funny thing is that even though we have here g, lambda, these parameters, on top of that, this h is the thermal h given by the number of thermal degrees of freedom g star, and all the things. In reality, this whole stuff has only one real parameter. I mean, like dimensionless parameter tau star, and the equation of motion looks like this. So if you stare at this equation, you see a very interesting point that this tau star suppresses all your derivative terms. So it's like similar to WKB, actually, approximation. So if tau star is large, in that case, we can trace the minimum. If tau star is small, then we are beyond the adiabatic approximation, and we cannot sit in the minimum. So the physical meaning of this parameter tau star is exactly, it turns out to be the ratio of the bare mass to the moment, to the Hubble parameter at the moment of time when effective mass goes to zero, or if you want, roughly speaking, of inverse phase transition time. So now what is good about that, because on one plot we could write solutions for different parameter values. And this can be done in this renormalized or rescaled by, let us say, field chi bar. So basically, which is now in units, of course, of m, but also you use square root of lambda. But for time, it's better to use, of course, this tau star, and on top of that, of course, m. So basically, there is some stretching. In that case, as you see, when this dimensionless time is roughly speaking 1, that's when you expect that this phase transition happens. In reality, as you see, these two trajectories detach from each other at times slightly less than 1. So basically, slightly before. And after that, as you see, the amplitude just decays, and it's very easy to see that it's, I mean, numerically, maybe I should next time do the envelope, that it goes properly as a minus 3/2. And of course, we're interested to see in case when this tau star is much larger than 10 or 80 or whatever. So basically, this is the picture of this dynamics. And now let's do the following. Let's assume, so you see, so far, we could entertain this idea for different masses and different coupling constants. But let's assume that actually the whole dark matter is in this chi. In that case, we can just estimate what should be the mass, right? That fixes us the mass in terms of other parameters. How can we do it? Well, we say that at the moment of equality, which we don't want to change, rho chi is equal to the epsilon of radiation. Then we just need to calculate properly the redshift using the standard entropy conservation law. That gives us the redshift. between the moment of inverse phase transition and T equality. And now we make this basically rho dark matter to be equal to epsilon radiation at T equality and obtain the mass. So the mass is given then by this kind of ugly formula, but you see from what are the dimension-full quantities which are running the scale there. And what is also interesting is that the parametric dependence of this mass on self-coupling constant lambda is this 3/5, and on this portal coupling constant is just inversely proportional. And I see like T equality is 0.8 eV, so therefore it's not a big surprise that this mass is roughly speaking 15 eV if you normalize it to proper scales you are interested in, proper values. So now they appeared this beta. So what is this beta and why? This is the formula for the mass was so simple. It was 1 over g, and now you see the g power 7/5. So what's the deal? So the deal is that we are interested, as you see from this normalization of g, in really small coupling constants, portal coupling constants. And beta is actually nothing else as lambda divided by g power 4. And why have we introduced this combination? It's because this beta should be always larger than 1 over lambda phi. So lambda phi is a self-coupling constant for this thermal degrees of freedom phi. And the point is that just from Sylvester criterion, if you want that the potential is bounded and there are two quartics and cross quartic, right? We want that this g is actually less than the products of these two lambdas. I mean, g to the 4. So therefore, if you want that lambda phi is actually less than 1, so that we are in perturbative regime and can talk about all this, then beta should be always larger than 1. So therefore, in this formula above, for the mass, we split the contributions, which are basically this beta and larger than 1, and g, which is always tiny. So now let's see what can we generate. So we fix the mass in terms of these two coupling constants, let's say beta and g, and well, these two dimensionless parameters. And now we can plot where can we actually generate this dark matter in this scenario. And this turns out to be very, very interesting. So it's a huge parametric space. So you see all this, so white region in space of mass of this dark matter particle and the portal coupling constant is actually huge, because you see it starts below freeze-in, because if it's above freeze-in, then we will produce everything. So basically, if it is freeze-in, we will produce everything by freezing. And if it's above, it just doesn't work. Then somewhere even above for larger coupling constants, there is freeze out, but for much higher values. And then why it is a white space? Because on the left, you have the border when beta becomes less than 1. So then we are off the perturbative regime, right? And to the right, there will be the moment when you cannot hold on the conditions that the mass should be larger than h. So basically, there is a border. And this corresponds to very, very large betas, okay, and some coupling constants. So you see, from the left to the right, beta increases, and formally speaking, you can even entertain such ideas because beta is lambda divided by g power 4, and you consider very small coupling constants for both of them. This beta, formally speaking, can be as crazy even as 10 power 16, but okay, this is a bit extreme. So this is really huge chunk of parameter space. As you see, freeze-in mechanism would be just a line there, okay? And here we are going orders and orders of magnitude below that. So now what I'm going to tell you in the second part of my talk is that actually in this part of parameter space, this mechanism does produce gravitational waves, which are actually observable. potentially. I mean, like in the future experiments. And it's also interesting because actually this parameter space, this white space, extends to crazy coupling constants like 10 minus 18. And don't forget that the true constant written in quartic term is actually g squared. So basically what we are talking about is dimensionless quantity 10 minus even 36 there. Okay. And masses, which can be really, really small. So it's here, it's in keV, in kilo electron volts. So that can be up to 10 minus whatever, 15, 16 keV, right? So basically 10 minus 12 eV, 10 minus 13 eV. Well, actually, maybe even lower, but honestly speaking, if you go to very low values, in that case, this inverse phase transition starts to happen during the BBN. And then it depends on your courage and bravery, whether you want to allow it or not. Okay, so now let me, so basically this is the mechanism. This mechanism is predictive if you assume that the field work traces this vacuum, okay? So now one can ask, okay, what was there before? And you can think as the only way, okay, this immediately starting from reheating, there was hot temperature, this tachyonic mass appeared, so the scalar field would like to go from most probably an unbroken minimum, right, to either left or right. And the point is that mu is much, much, much larger than m. So practically this m can be relevant. And in that case, one could think that this happens very quickly, this transition either to the right to the left. But in reality, not really, because if you sit on top of this potential, but your Hubble is huge, you cannot move. You are in a kind of slow roll regime. So therefore, the moment when you start rolling down properly is when this mu is approximately h. And it still takes a bit of time, but this in this simple version, we will neglect it. In the longer paper, we actually consider the rolling factor. This introduces some basically more freedom in a sense in the parameters. Okay, so but roughly speaking, let's think that it starts rolling and that this rolling is pretty fast. In that case, we would know when the field takes the value either to the left minimum or to the right minimum. And that's the moment when this mu is equal to h. This can be very easily calculated, so that corresponds to the temperature, which is g multiplied with m Planck. Don't forget our g can be 10 minus 18, 10 minus 16, so it's quite early in the universe. And of course, when field takes either right value or left value, that implies that you create domain walls. So usually domain walls, people like to write for this potential, the quartic one, with this shifted kind of quartic part, if you want, by this basically eta. So eta is your expectation value. So in our case, eta is just, so eta squared is just mu squared divided by lambda. So you can just recall that eta is just proportional to the temperature. That's the most important thing. So eta is temperature up to a constant. So now why it is important? Because the thickness of these domain walls is inversely proportional to eta, right? So therefore, our thickness of these domain walls is inversely proportional to temperature. So another thing what is also important is that for normal domain walls, for standard domain walls, this eta is just a constant. Okay, so usually people consider eta as not time dependent. Okay, so now one can calculate actually the standard formula, what is the tension of a domain wall, and it's actually proportional to eta squared, or in our case, the tension is T power cube. Okay, so now we assume the standard mechanism works so that the network of these domain walls enters scaling regime extremely fast. And that's what was introduced by Keeble in 1976. And in that case, everything is actually very simple. So they will be like one or two domain walls per Hubble volume. And in that case, everything is defined by actually this tension and Hubble. So basically, in that case, the mass of domain walls is just sigma wall multiplied with surface. So basically divided by Hubble squared. Then the density is the mass multiplied with volume. So that basically, divided by the volume, it's mass, right? So divided by the volume, so therefore multiplied with Hubble cube. So therefore it's sigma wall multiplied with h. And now you could see immediately from there that our density in the energy density in the domain wall networks is actually much less than the energy density of radiation because our beta is always larger than 1, and we can think that n is not too huge. Okay, so basically, effectively, this formula introduces you bound on number of fields which are allowed there in this thermal multiplied phi. And the interesting thing is, if it is less than 1 at the beginning, then after that it just decays as temperature. So therefore, if it was not a dominant energy source for the universe at the beginning, at the moment of basically creation of these domain walls, then it stays subdominant component forever. So basically, we don't need to care about it. Okay, so now what was surprising for me, really surprising, is that the gravitational wave production of such domain walls works practically as Einstein predicted. So you take the quadruple formula, and you can easily estimate with a quite good accuracy the power emitted by this domain wall network. And it's, for me, it's quite striking because usually this formula is derived under like very certain condition of non-relativistic matter in wave zone and all the things. So now it still works even for those distributed sources. And why we say that it works? Because it was calculated in this paper for normal domain walls with constant tension. And people studied how these domain walls would emit gravitational waves. So basically what you say is that the quadruple moment is just, of course, roughly speaking, that was this mass multiplied with radius squared. So our radius is 1 over h in the scaling regime. So therefore it's m wall divided by h squared. Don't forget that m wall is sigma wall divided by h squared. So therefore the if you want, of course, this derivative of the quadruple, the third one, you also multiply with h every time, right? So therefore, if you calculate now what is the energy density in gravitational waves emitted in this way, it becomes just their tension squared divided by m Planck. Is some coefficients, but coefficients are like some numbers. So for normal, you see, the interesting thing is for normal domain walls, this gravitational wave density is constant. But for ours, it actually drops down because sigma wall was proportional to eta cube. So therefore, this raw gravitational wave scales as t power 6. So it's really redshifts very fast. So moreover, what is interesting, so what these guys have seen, that the scaling regime indeed is attained almost instantaneously. It's a very quick process. And that for them, the peak frequency, because you see the gravitational waves have constant energy density there, then of course, with respect to the redshifting radiation in this omega, which I will introduce just the next slide, the most important part is when you can kill domain walls. They kill it by just explicit breaking, and therefore for them the peak frequency is, if you want, the maximum of this omega. So it's the latest time. But for us is, of course, the earliest time. So basically when they create. So basically peak frequency is Hubble, and basically what they saw there in the simulations, that the log derivative of rho gravitational waves with respect to the frequency is given by basically the formula I showed you before, just with these two corrections, which will be longer to explain. So one A is kind of what they call area correction, but it's a number. And epsilon is efficiency correction. But as you see, these from the numerical simulations, both these factors are order 1. So now if we go to what is called this spectral density, basically normalized spectral density. So d rho GV by log interval and 1 over total energy density. In that case, we can estimate when is the maximum, when is how does it look like. And you see, so we know that in the case studied by these colleagues of us, this quantity, of course, because rho total decreases as t power 4, in that case, and they d rho over d log f is basically constant because the sigma ball is constant. In our case, this is not true because in our case, this is t power 6. So basically, we need to take the peak at the beginning. Okay, so now the point is that if you plot the frequency at the peak of this quantity omega, and then we estimate it using the simulations, then what we see is that the frequency at the peak is, roughly speaking, 60 hertz, square root of the number of degrees of freedom, and then just your coupling constant. So basically, but don't forget, in the proper portal, in the Lagrangian, we have g squared, okay? So basically, our frequency is just given from one parameter of the model, just through this portal coupling constant. On the other hand, if we calculate this omega gravitational waves, this normalized spectral density, now, of course, this frequency is frequency now, okay? And we plug in all this redshifts and whatever, we see that it's just inversely proportional to this beta squared. So beta is always larger than 1, g is always tiny, like less than freez-in, and for freez-in, g was roughly speaking like 10 minus 6, 10 minus 7. So you can see what it is. So then we used what is called GV plotter, and we plotted what is called S. So S is this power spectral density. And then we compared it to planned missions, to planned experiments or observational observatories, better to say probably, which are going to measure gravitational waves. So here we plot only peak, right? So therefore, as you see, we can just scan. So we fix beta, we fix number of degrees of freedom in the thermal guide, and then we scan over different G's and look at the peak of this of the signal in terms of omega. So then we need to plot this SH. So you see S would be inversely proportional to F cubed. Okay, I mean out of multiplied with this omega. So what is important that as you see, if you have beta, roughly speaking, 100, then you are on the edge. So it's very hard to measure. If beta is less than 100, then your signal is above and can be actually measured either by LISA or by DeSiger or by Einstein telescope, depending on your portal coupling constant. It can be even measured by IPTA or SKA, potentially. but that requires very small coupling constants. So now let's recall what are our masses, and you will see that potentially observable gravitational waves are, roughly speaking, for masses less than MeV, and then this coefficient G divided by 10 minus 8 power 7/5. So in particular, that implies for the region which could be measured, observed, better to say, by a laser, your M is, roughly speaking, 10 minus, like in the center, like 10 minus 5 eV, and G goes from 10 minus 14 to 10 minus 11. So 10 minus 5 eV, that would be nice for axion, but of course, what we are considering is not an axion. And so this is quite interesting, that you see, by just looking at frequency of the gravitational waves, we will know about this portal coupling constant. So one should say that the observable range of this portal coupling constant is tremendous. It's from 10 minus 8 to 10 minus 18, roughly speaking. On the left edge, you just move this inverse phase transition almost to BBN. So that's a bit shaky, but you know, it doesn't mean that you necessarily spoil the BBN. It just requires a bit more thought. Okay, and a bit more speculative, we try to estimate even the spectral shape. Okay, the proper spectra of these gravitational waves. And basically what we claim that in basically there is this peak frequency, that's true. And as you see, this peak frequency is when this slope, don't forget, this is this S, right? This S, so therefore it's 1 over F cubed. So the peak corresponds to when the slope changes, right? The first bang. And in UV, so basically in this, there is a cutoff which corresponds to the thickness. And that's our first difference with respect to constant domain wall, because our cutoff moves with time. So that requires a bit more of investigation. But there is a sharp cutoff, okay? It's because, of course, this domain wall network doesn't emit gravitational waves on scales shorter than the thickness of these domain walls. And our domain walls are getting fattier and fattier. Then after that, there is no reason for us not to believe in UV calculation, because there, this UV gravitational waves, we probably would not care about whether the tension was time dependent or not. It's irrelevant. So therefore, this omega GV is just 1 over F there. So that we see from the sharp cutoff, that's the first change of the slope. And then there is a peak. And the second change of the slope is actually interesting, because we think that in IR, these are the gravitational waves which are emitted slightly later than the formation. So, well, because it's not on the peak, but it still gets emitted. And roughly speaking, it gets emitted still with Hubble frequency. So therefore, in our case, this omega GV, if you look at this formula before, it's here. Just give me a sec, I will show you. If you look again at this formula, let's say, well, you can think that this H rho total is here H squared. So you basically would see that that if our frequency is roughly speaking H, right, then in sigma wall we would have we had this T power 6, right? And then in this rho total, it was T power 4. So it's basically T squared. So therefore, it's basically, if you look at it at the end, it becomes, after rescaling, it becomes F squared. So interestingly enough, because in their case, the tension is constant, and there's a different basically motivation for these domain wall networks. In their case, this omega is F cubed. That's the difference which we can see, because in our case, it's just emission later. And in their case, it's something else. So basically, this is our tentative suggested spectral slope for the signal. And as you see, we can still like enter to, depending on the coupling constant, we can enter into the sensitivity regimes of different future experiments. So I think this is very interesting, and I think this is a highly promising path to the origins of dark matter. As you see, this picture I have taken in Kyoto, and it's kind of, you see, hidden germ, hidden very nice garden. Maybe it's even in paradise, but a small one. So thanks a lot for your attention.
Okay, thank you very much for the nice talk. Are there questions or comments?
So I have a question. So
Perfect.
yeah, thank you for nice talk. So I actually, I listened to your talk in Kyoto, so last year. And
very good.
yeah, I have a question about the number of degrees of freedom, capital N. So in your model, I think phi is massless, right?
No, phi can have a mass, it's just not relevant in the regime which we consider, because we want that the inverse phase transition and direct phase, of course, direct phase transition in that case automatically, that the inverse phase transition happens when the temperature is much larger than the mass of phi. So therefore,
Okay.
phi is not dimensionless, but effectively dimensionless.
I see. So at the high temperature, so phi is effectively massless.
Yeah.
But as the temperature decreases, so phi becomes massive, and it causes no problem. Is
Yes,
that correct?
yes, absolutely. You're absolutely
Yeah.
right. So therefore, we avoid the bounds on effective number of degrees of freedom. Yes.
So that's what I wanted to ask. So we
Yeah.
have a constraint from BBN and CMB about the number of degrees from them. Okay.
Yeah. No, this
Thanks.
is avoided because for us it's thermal during the processes we consider, but it's not after that. So you see, therefore, it's kind of what I wanted to say is that if you go to really low coupling constants, like it's here, if you want, like to this really corner, which is the picture there, kind of zoomed there. If you see, if G is 10 minus 18, you can see that the inverse phase transition temperature becomes really too slow or too small. So you see, this M is your mass, right? This, basically, you can maybe better see in maybe direct phase transition. Yeah, you see, in direct phase transition, when the main world network is formed, this M is 10 power 19 GeV, right? Okay, 18 GeV, because here we normalize it, I think, to 8 pi. And here, if the G is 10 minus 18, then basically this becomes, roughly speaking, GeV. So it's not great, because this is for direct phase transitions, and the inverse one happens later. So therefore, basically, this would be a bit on the edge. Or you would need to increase N and then play this game, but that's maybe a bit too much.
Yeah, thank you.
You're welcome.
Can I have very nice questions? I'm not familiar with dark matter physics, so can I understand your mechanism as like let's say, so you realize the misalignment mechanism by the inverse phase transition?
Absolutely. Absolutely. It's just
so
we have actually prediction of the amplitude, so where it is.
So one more question is that have you also considered that your phase transition is related to and U1, not Z2?
Actually, Sabir entertains this idea and looked at cosmic strings. And they have
exactly.
paper with Samantha Rom and probably just with Samantha Rom. And if you want, I can send you a link, but it's one of his recent papers. So he also studied the network of cosmic streams.
Thank you. Thank you very much.
You're welcome.
Could you, maybe this is a too naive question, but could you explain a little bit about how the mechanism of the gravitational wave production from the domain world? That
Look,
talking about from quadrupole moment, time dependent. So the quadrupole moment.
it's basically time-dependent quadrupole moment. It's actually really striking that this mechanism works. So basically, the normal Einstein formula that quadrupole third derivative squared gives you, roughly speaking, the power. It's quite strange, I would say, but you see, by estimations, it kind of works, but then people do numerical simulations. I mean, these guys, yeah, it's quite surprising that it's that robust. It's hard for me to say more because you see, what we are lacking is a really proper numerical situation for our case when the tension is time dependent.
So I mean, sorry, please.
Yeah, go ahead.
So in the, for example, in the case of the strong first order phase transition, there are some, I mean, for example, bubble collision and etc. They produce a source of the gravitational wave. But here you don't have such a thing, or do you have such?
It's kind of different because it's the domain walls. They kind of they move, they intersect. When they intersect, they disconnect, whatever. They try to kind of make a kind of bubbles also. These bubbles kind of collapse. I don't know. It's kind of complicated dynamics. How to visualize it? It's I cannot say I feel very easy, because one should imagine space which is very inhomogeneous on huge scales, and then these walls kind of try to, first of all, they move by trying to keep, if you want, the scaling regime, and then they also basically change their surface, like similarly to what is happening with strings when they reconnect and do. But with strings, it's very complicated business. As far, I'm not a specialist at all, but as far as I remember, it's really hard because people are discussing what happens with different types of reconnections and cusps and kinks and God knows what. So it's I wish I could visualize better how does it work, because here we really rely on the results of the simulations.
Actually, I attended the DSU conference in last month in Melbourne, and I listened to your talk, and I wanted to learn more about your talk, so I suggested to invite you to the seminar organizer. Yeah.
Great. Thanks a lot. I hope you learned more.
Yeah. Thank you.
I have a question. What's the reason why the green region of gravitational wave upper bound is given around 10⁻⁷?
Oh, three slides ago. Slide 13.
Slide 17. Okay, so what's the
13. Page 13.
Page 13. Okay. Oh, what's the sorry? What's the reason for what?
Gravitational wave.
You mean this? Why it is confined in this green stripe, right? Because you see,
around 10⁷. So why?
Yeah. Because you see, so it's roughly speaking, it's 10⁻⁸ in G, and you see the gravitational waves, of course, produced in all this white region, right? The point is just for observable gravitational waves, because you see 10⁻⁸ it's roughly speaking, you go to the Einstein telescope and so on. But after that, it just goes down, and that's it. So it's basically it's if you want observable region for gravitational waves. Not otherwise, of course, this network always emits them. That's not a problem. So they're always there. Just the question is whether we can see them or not. So basically, nothing really radical happens if you take G to be, let's say, 10⁻⁷ or whatever. But you see, on the other hand, one should say that if G is slightly larger than 10⁻⁶, then you are in freeze-in. So basically, sorry, if you're much like basically if you're between, let's say, 10⁻⁷ and closer to 10⁻⁶, so closer to this line when freeze-in operates. Then, of course, you have admixture of now freeze-in particles and the dark matter particles which you generate there. So therefore, if you want to keep that this mechanism is a dominant one, of course, you need to go a bit down. I mean, if you want to use these estimations, because otherwise freeze-in will be dominant, of course. So therefore, you see, we would not be able to go much to the right in this plot. Just because, you know, when you go, okay, 10⁻⁷ maybe, but okay, beyond 10⁻⁷, you need to do completely different analysis.
Here, G and beta is kind of free parameter.
Yeah, both G and beta are free parameters. They're just chosen. You see that you know that this omega gravitational waves is always in a sense less than what beta divides. And in F gravitational waves, you see that just it's normalized by this 10⁻⁸, so that G is less than freeze-in, and which is and has an interesting, so to say, values for observations. So if you want our frequency of gravitational waves which we want to observe is always less than 60 Hertz. Well, multiplied with the square root of number of degrees of freedom there.
You mentioned that you plotted a peak of gravitational wave. Could you explain what is the shape of gravitational wave if we fix one parameter?
Yeah, actually, see, I also discussed it with Guillaume de Deminay. I don't know whether you know him or not. And he pointed me out some interesting paper where people are talking about integrated signal. And that actually would allow us to, of course, if you integrate the signal, it's more observable in a sense, right? So that basically allows you to go to much larger betas. So even to suppress this thing more. So beta would not be 100, would be probably more than 100. But you know, that would require more careful analysis. So I don't know to which extent. So you see, peak is kind of more or less safe side, right? But if you go to integrated signals, then there it would be nicer to have proper numerical simulations for us. I mean, for this system.
So I remember Professor Hiramatsu studied about such a numerical simulation of domain.
Yeah, exactly. That's what I'm referring to. It's Takashi Hiramatsu. But as you see, as far as I remember, so he doesn't have another paper where he would study this more complicated, I mean, setup similar to ours. So basically in this setup, the domain wall network has, basically the domain walls have fixed eta, so fixed fixed tension. So you see fixed eta is fixed sigma. And then the domain wall just disappears because you just introduce a breaking, and basically it just goes away. But it's a bit different. So of course, if Hiramatsu-san could do a simulation for this would be amazing. Or explain to us how to do it. But from what I heard from my Japanese colleagues, Hiramatsu-san was very good in doing these simulations. So what can I say?
Mhm.
I hope when I'm next time, I maybe can persuade him to do this. Or learn from him how to do it. That would be, of course, even better. But yeah, what can I say?
Other questions or comments? Otherwise, we may thank the speaker again. Thank you very much.
Okay, guys, thanks for inviting me. It's a pleasure. And yeah, thanks for good questions.
Thank
Okay.
you.
Have a nice day. Bye bye.
You too, and guys, Happy New Year. A bit
Happy
too
New
late,
Year
but
to you too.
still actual. Okay, ciao, ciao. If you have any questions, feel free to write me.
Okay.
Okay, have a nice evening too.
Mm-hmm.
You too.
Ciao.
Thank you.